Hello guys, welcome in this new video. So in this video we will be discussing about the handshaking lemma, and also we will discuss about the enumerations in binary trees. So with no further delay, let's get started. So if you haven't checked the previous video where I discussed about binary trees in details, so do check it out as well. Now we are moving further ahead with that one. So let's get started with no further delay. So basically what is the handshaking lemma? So it is generally for the graphs data structure, but you do not need to worry because we will cover the graphs data structure as well, but as it is required in here, so we are just discussing it. So basically it tells that an even number of vertices will always have an odd degree in every undirected graph, okay, that is finite. So what we can actually get it from here is that if we sum all the degrees of every vertex in our tree, then we will get the number equal to 2 times the number of edges in that tree. Okay, now to prove that, you can check that if you see the number of edges, then they are 1 2 3 4 5 6 7 8 9 10 11 12. Okay, so there are 12 edges, and if you sum all these, then that should be equal to 2 times 12, that is 24. So let's check the degree of 1. So it is 2, so 2 plus degree of this one is 3, so 3, that is 5, 5 plus 3, that is 8, and again plus 3, 11 plus 3, 14 plus 2, 16 plus 2, 18, 19, 20, 21, 22, 23, and 24. So this proves that this is a correct thing. And now this lemma is useful in tree data structure as follows. So in a k-array tree, k can be a binary, bi, tri, quad, okay, like that. So as I discussed binary tree, where we can use the internal nodes to find out number of leaves. So I discussed this in the previous video as well, but here they are generalizing it as a k-array tree. So we will see that if we just subtract 1 from that k-array tree, that is, let's say there are 4 k-array tree basically means that the node present in that tree will either have 0 or k childrens. Okay, so let's say there is a trinary tree, that means it is having 3 or 0 children, okay, for every node. So here 3 minus 1, that is 2, into number of internal nodes plus 1 will be equals to the number of leaves in that particular tree. Okay, so you can also see the proofs here, but it is just that it will prove this one. But one thing is that you can see here is that in binary tree, a number of leaf nodes is always one more than nodes with 2 children. So basically it is telling that the root plus the internal nodes will be 1 less than the number of leaves, or we can generally say that number of leaf nodes will be 1 more than the nodes with exactly 2 children in a binary tree. So this was also proved by me in the last video, and you can also see the proofs here. And now let's get to the enumeration part of the binary tree. So enumeration of binary trees is basically known as either having the labeled binary tree or an unlabeled binary tree. So unlabeled binary tree is a binary tree that is not having any label to its nodes, and a binary tree that is having labels to its nodes are known as labeled trees. So these two trees here are unlabeled and they are equal, but these two trees that are labeled are different from each other. So how many unlabeled binary trees can we have with n nodes? So basically for that we have to first understand what are Catalan numbers. So Catalan numbers are the numbers that follow a particular sequence, like 1, 1, 2, 5, 14, 42, 132, and so. So this basically follows a formula like sigma of, that is summation of all the i's starting from 0 to n minus 1 for this formula ti tn minus I minus 1. That will lead us to this Catalan number. Okay, so if you also see, let's say these are starting from 1 and 1. So if you want to find out the second numbered Catalan number, so you can, what you can do is 1 into 1, then again 1 into 1, so double of this 1 into 1, that is 2. Okay, now one more thing to keep in mind is that you should always start it from t0, not from t1. Okay, now coming, let's say we have to find t3. So what we can do is just double this 2 into 1 and again 1 into 1, so we will get 4 plus 1 into 1, that is 5. So we will get this one. Okay, now let's say we want to find t4. So what we will do is we will first multiply 1 and 5, then we will multiply 1 and 2 and just double them. Okay, so what we will get is 5 into 1, that is 5, into 2, so that is 10, and then we will multiply 2 and 1, so 2 into 1 is 2 and doubling that is 4, so 10 plus 4 is 14. So now this is the formula, and you can also find the nth Catalan number using this formula. So basically it means that this actually the number of unlabeled trees that can be found from n nodes is exactly equal to the nth Catalan number. So you can find out that using this formula, 2n factorial divided by n plus 1 factorial into n factorial. Okay, so this was a very important thing to be noted. Now let's say there are n unlabeled trees. Okay, so how many labeled binary trees can be there with n nodes? So we can use this this above formula, this one Catalan formula, to actually find out this, because see, to count labeled trees we can use above formula, like every unlabeled tree with n nodes can create n factorial different labeled trees by assigning different permutations of labels to all nodes. Hence, if we just multiply this n factorial with the nth Catalan number formula, then we will be getting our total number of labeled trees. So this is the answer. Okay, now let's just see some other applications that were not covered by me in the last video for these trees. So they basically store hierarchical data like folder structure, organization structure, XML or HTML data, and binary search tree, that is BST, is a tree that allows fast search, insert, delete on sorted data. It also allows finding closest item. Now these two were actually told by me, but from here to here this was not told by me. Okay, so just discussing that one. So heap is a tree data structure which is implemented using arrays and is used to implement priority queues. Okay, and B tree and B plus trees are used to implement indexing in databases. Also syntax tree is used in compilers, and KD tree is a space partitioning tree used to organize points in a k-dimensional space. And tries are also used to implement dictionaries with prefix lookup. Trie is basically a type of tree only, and suffix tree is also used for quick pattern searching in a fixed text. And the spanning trees and shortest path trees are used in routers and bridges respectively in computer networks. And as a workflow for compositing digital images for visual effects, this tree's data structure can also be used. So now coming to the insertion in binary tree. So basically first we have to see what is a level order traversal of the tree. So level order basically means that we traverse the tree via level by level. So we will first take the 0th level, then elements in the first level, then elements in the next level, and so on. So basically the traversal in level order will be like this: 10, 11, 9, 7, 15 and 8 in this tree. So if we have to insert any key or any element in a binary tree, then we will insert that element in the first position available in the level order. So as you know that if we go through this tree in level order, then we will find the first position that is empty is this one. So if any element has to be inserted, then that element will be inserted in here. So if we insert, let's say 12, then it will be inserted here and the tree will look like this. And now again, if we want to insert any new element, then it will be inserted to the left child of the 7, that is in here. Okay, so this was just how we insert any element in the trees. So you can also see the implementation in different languages as well. And yeah, so now coming to the deletion part in the binary tree. So basically we can delete the node from that binary tree such that it makes sure that the tree shrinks from the bottom, which means if we want to delete any node, so we will replace that place by the bottommost and the rightmost node. So this is basically different from the BST deletion, that is the binary search tree deletion. And as here we do not have any order among elements, so we replace with the last element. So let's see an example to understand it better. So if we want to delete this 10 from this tree, then what we will do is we will replace this position with the bottommost or the deepest node in the tree and the rightmost node in the tree, that is this 30. So we will replace this with the 30, so it will become 30 and we'll have left child as 20. Now for another example, let's say if we have this tree and we have to delete 20 in here, so we'll replace this 20 with the deepest and the rightmost node in the tree, that is this 40. So we will replace that position with the 40 node, and like this we can delete any node in the binary tree. So you can also see the algorithm in here as follows, and this is what I have just told you, and you can see different implementations in different languages. Also one more thing to note is that we can actually delete a node and replace that node's data with any node whose left and right child points to the null. Okay, but we use only the deepest node and the rightmost node in order to maintain the balance of a binary tree. Okay, and one more thing is that, let's say in this tree, this 10, 20, 13, 40, if we wanted to delete this 40, then we have to just delete it, and we do not want to replace it with any other node because it is already the deepest and the rightmost node in this tree. And this was all about the deletion in the binary tree, and till the next video, keep watching and keep learning.